Okay, so heading into the final project here, I'm going to go through, I'll start it off by kind of going through the engine features, the new engine features first, and then kind of going from there and showing off my project, which is the GAM Plus. So starting with our collision system, which probably got the most changes out of anything. One of the big changes here is that now we have multiple collision volumes that we're processing. So originally we had our B sphere, which was the only collision volume. Where we passed in, and essentially we just need to figure out what the radius and the center to calculate those, kind of like before. Now, what is new here is that we have these visitor functions. Basically, whenever we want to test if there is one collision volume coming in, we'll basically call the respective functions to figure out, okay, which intersection function to call. And then all the actual intersections are only done inside of the math tools, which I'll demonstrate shortly. But the B sphere by and large is the same. The AABB and the OBB are the new ones that we're looking at. So ABB, we only really need to worry about the min and max. We basically have to recalculate that every frame because the min and max are local on the model. So we basically go through each of the vertices, figure out the min and max from there. We also calculate some other data, such as the local center, local matrix, the diagonal, which is the diagonal from the center to its corner, as well as its world matrix as well. That is for the collision data, which I'll be demonstrating shortly. And then very similarly, the OBB basically kind of figures out the same data there as well. And basically how both of those are processed, since they're both very similar, both the OBB and the ABB inherit from a bounding box base class, essentially with the references to all of those variables there in order to be able to get those for the collisions, because their collision processes are actually very similar. So with the collidable class itself, since we do have these multiple options now for a collidable volume, the user is able to select which object that they want to do. So just as an example, if I went into one of my objects here, just to kind of demonstrate that. So let's say for our player. So right now we have the OBB set. If I change this to AABB for instance, and then also use our visualizer for our AABB. So basically, we can go ahead and pass in the AABB. The user gets to specify which collision volume they want for their object. So if I skip to a scene here, we can see an AABB that's forming around our tank, and that's all working properly. And then if we want to go ahead and switch that to a B sphere, then that should be able to work as well. Great. Yeah, that's showing up there as well. Awesome. Okay, so basically what is happening there is that based on the enum value, we'll go ahead and create a brand new collision volume based on that. And then also by default, every object that's created with the collidable will also go ahead and create a collision volume B sphere to help with the tiered collisions, which I'll be getting to shortly, just to kind of help make them a little more efficient. But just demonstrate that that works. So going back to the collidables itself, was there anything else that really changed? When we update the collision data, we'll update both the collision volume and the B sphere, of course. Let's see, I think that's basically that. Now for the collidable group, the big change that we got implemented is that each collidable group now holds on to their own AABB to help, again, make the collisions a little more efficient. So basically, once every frame for each collidable group, we will go ahead inside of it and recalculate its min and max variables, essentially getting them from going through each of the objects inside of the collection, getting its B sphere, and computing the data from there. So essentially, we'll kind of get the radius and the center positions and kind of calculate a good enough AABB from that data there. and then we'll recalculate that once per frame for each collidable group. So inside of our collision manager, when we actually process our collisions, for each collidable group, calculate its ABB, and also visualize that ABB, AABB as well. And the visualizer now is actually command-based. I'll be able to demonstrate that shortly. But yeah, I think that's basically it for the for the collidables. Now for the collidable registration commands themselves, we've made some modifications to these as well. So for when we test a pair of objects against each other, we now have 4 tiers of testing. First, we check to see if the AABBs of both collidable groups are intersecting at all. Then we'll check for each object in the first group, see if its B sphere intersects with the AABB of the second group. If that's the case, we'll check the B spheres of 2 different objects, see if they collide, and then we'll finally check to see if their collision volumes actually collide. And if they do, we'll go ahead and process the collisions for that. So just to demonstrate that this is working, for instance, I will put a breakpoint on checking for the B spheres. This should only be called once the 2 objects that are being tested are actually going to be, this should only be called once the collidable group AABBs actually intersect. So as an example, the bullet that I'm going to shoot, we want to shoot it at these targets here. That breakpoint should only be called once the ABB actually, once the bullet comes into contact with it. Yeah, there we go. So that gets called. So as before, where it was always checking it every single frame, now it's a little more efficient with checking it there. So that's all set. And then similarly for the self-test command, we only need 2 layers of testing. Basically, we'll check if the B spheres collide first of both objects, and then we'll check the collision volumes there. So I think that's it for the collidables itself. Yeah, user selectable. Have our collision volumes that we go through there. And again, OBB and AABB both inherit from the same class and use the same kind of variables, so I'll demonstrate the collision there. Collidable groups, collision manager, collision tests. Great. Okay. And then once I get to the math class, I'll show the math behind the collisions themselves. So the visualizer, heading into that, there's kind of several changes. The biggest change here now is that I was able to go ahead and set that up as a with a command pattern, but I'll demonstrate that here real quick. So the visualizer, we basically have our different functions to register our different collision volumes going through there. And then essentially with the command pattern, whichever one we create, we'll either create a box command or a sphere command, whichever one we need. We'll pass in the matrix and the color, and then use the respective graphic object, which is only held onto by the visualizer. Basically, we'll go into our command base factory and create a new command base. And when we create that, we assign the variables. And then once it comes time for the, we also go ahead and add that command to the visualizer broker. We go ahead and add that in here. And then every frame will execute the commands and recycle that command base so we can keep reusing it. So essentially when it executes, that's when that gets called there. So I think that is basically it for the visualizer. Let's see. Oh, and there is also the colors. I do have the colors now, which I didn't have before, but basically just the static list of colors, and then we go ahead and initialize them there, so that's set. Okay, I think that's it for the visualizer. Now let's go ahead into the math tools, just checking the time here. Okay, so math tools, we have a lot of changes here. Most of the work is with the intersections themselves, but we also have a lot of smaller functions to help out with some more common tools that we might want to use. But I'll mostly be focusing on the intersections here. So again, the collision volumes, when we have the collision volumes, again, we use the visitor pattern to figure out which function we should actually be calling. The B-spheres is the same as before. We basically just get the distance between the centers and figure out if that is less than the sum of their radii. Now, with two AABBs that are two AABBs intersecting, we'll check if the first one's max is less than the second's min, or vice versa. If that's, if that either of those are the case, then they do not collide. Otherwise, we will return true. So that's pretty straightforward. OBB and OBB I'll get into shortly. As for AABB and OBB, again, just because they're so similar. Now, intersections between a B-sphere and an AABB, fairly straightforward. We basically clamp the B-sphere to the box. We'll get the closest point there, and then we'll calculate the clamp point minus the B-sphere center. So if the dot product of that is less than the sphere's radius squared, then the objects do collide. And then for the and then for the OBB and the B-sphere, it's basically the same thing. The only conversion that we have to make, we essentially convert the OBB first to an AABB in local space, essentially. And then essentially we just kind of process that as a B-sphere and AABB collision. We'll get the clamped point and figure that out and determine the data from there. And then here's just some of the other helper functions, all pretty small. Now, intersect BB is for the AABB / OBB collisions. So basically, we will get the local axes for each of those objects, and we will use the separating axis theorem test on 15 different axes. So each of the 3 local axes for each of the objects, as well as the cross products for each of them. If any of those overlap functions return false, then the boxes do not collide. So when we overlap, we're basically checking to see if the vector that we pass in, we're checking to see if that, essentially if the length of that vector, if it's less than the sum of the max projections of both A and B on that vector, to see whether they calculate or not. So calculating the max projection, we basically convert the vector kind of to local space, and then we go ahead and figure out the data from there, calculate the max projection, and then determine it from there. So I think that's pretty much it for the math tools. And then I think the last big one we'll be looking at is the terrain. So the terrain here, let's go ahead and start with that. So we do have our terrain object manager, pretty straightforward. It'll go into the textures folder, basically any variable that's passed in. So we assign the custom name as well as the height, the actual height map file we want to use, the max height, the length, the minimum Y value, the texture for the actual texture that'll be applied to it, as well as the repeat X and Y for how often we want to repeat the texture. So yeah, that's pretty straightforward, kind of a lot like the other asset managers we have. So the terrain object itself, when we go ahead and create that, we have the single object here. So we pass in all the data and then we go ahead and create our model. We just have one graphic object. So when we go ahead and create our model, we basically pass in the image data, get the image width and height to get the height data, and then basically we just go through each of the vertices, start in the upper left corner, go through each row. Now we will keep a list of the verts themselves. That's kind of helpful for the collision data and whatnot. And then in addition to that, we'll also, when we create the triangles, we also hold on to a list of min and max points to calculate the AABBs, which is helpful for terrain collision detection for each of the cells, basically. So I think that's the terrain object itself. And then going through some of the other big functions for it. So when we go ahead and align an object, so in my case, the hero tank is actually aligned to the object. So it's supposed to be using barycentric coordinates. Right now, I was not quite able to get this working quite properly, unfortunately. Basically, what it's supposed to be doing is that we essentially determine, given the position that passed in, we determine its position on the height map, kind of its pixel place, determine A, B, and C, the three vertices of the triangle that we're trying to kind of get the height data from. And then we go ahead and pass in, we go ahead and calculate our formula to get that height data and go ahead and send it back to our position. So just quickly going ahead and demonstrating this, just for some reason, the object itself, like in some cases, it almost seems like it is working, but in a lot of cases, it's almost like it's kind of doing the opposite of what it should be doing. Like here, like it sort of, not exactly sure what it is that's going on with it. I mean, it'll still rise up the hill okay, but it's on the way up there that's a little jagged, which isn't great. Okay. So that's that. And then the other function, so right now the terrain object actually does the intersection, collision intersection by itself. But basically how this works is that the collidable object that's passed in, what would really be inefficient is that we don't want the collidable to test every single cell of the terrain object. So instead, based on the size of the collision volume in the B-sphere, we'll essentially calculate the correct cells that we need to test it on to see if it actually intersects. So we'll figure out that range here, the min and max, and then for each of those cells in there, we will figure out the AABB from the min and max points we've held on to, and if the AABB and the collision volume intersect, then we'll call the respective collision terrain function there. So that is all set. And then also, again, just showing the test terrain command. When we go through each of the objects, we're testing it. Again, right now, the terrain object is the one that does the collision processing for the moment. And then I think there was one other thing. I'm trying to remember what it was. Let's see. Was there something else in there? Okay, and then just real quick. Yeah, and then basically when we go ahead and register that object for a scene, essentially what'll happen is that we'll, so just showing one of these scenes here. So we have a scene level function to set our terrain. We'll pass in the name of our terrain. We'll go ahead and go in here, create our variable that points to that terrain, and we'll go ahead and add it to our scene, submit it for entry. So yeah, it's pretty straightforward there. And then, yeah, I mean, I think that's basically it for all the new engine features. Was there anything else that I left out? I think I had shown, I don't know if I had shown this, but I did also get I actually didn't have the screen log before, but now I do have that. So the two different functions to pass in the strings, read in the arguments, convert that to a string, and then pass that through. I think I have my hero tank. The player should actually be doing that. Yeah. So I think I was demonstrating that already. Okay, yeah, so that's updating the position as we go. Okay, great. I think that's basically it for all the new engine features. So what I will do real quick then is I will go ahead and get this set up, and I will go ahead and get this set up and just quickly show off the game with the time we have left.